Okay, getting back to this diagram with the rumor graph, uh, this we can think of this value as the y value. If this is the y value, then that means those who have heard the rumor. Then those who have not heard the rumor will be represented by L minus y. L being the total number, in this case 2,000 students, minus those who have heard, right? If y is students who've heard, then total students minus those who have heard would indicate students who have not heard. And then this point here, this inflection point, is the rate when the rumor is spreading the fastest. We see that this is where the curve is at its steepest. Okay, for quantities y that grow logistically with the carrying capacity y equals L, we can state the relation mathematically in the following way. dy over dt is equal to ky times L minus y. We see that that matches with the rate that is the sentence that is given here. The rate is directly proportional, so we have the k here, to both the students who have heard, that's the y, and, so that's times, students who have not yet heard, so L minus y. So rumor is spreading at a rate that is jointly proportional to the total number of students who have heard and the number of students who have not heard it. Okay, so this is the equation that we're going to be working with for logistic growth. Now, this is the differential equation that represents logistic growth. But if we wanted to solve for y, this would be the solution or the equation. And we're not going to go through the work for this, but essentially, if we separate the variables and solve for y, we're going to be able to get to this equation. All right, if you see this on the AP exam, you want to be able to instantly connect these two, so it's best to just memorize this. Now, this is kind of a hard equation to memorize, and one teacher that has a memorization way to help remember this is this notation here, lice minus licht. So if we look at this side of the equation, this kind of represents, if you can memorize this, then it'll be easier to to write this equation, because you have L, and this is a 1, but it kind of looks like an I, so L-I-C-E, lice minus licht, so negative LKT. So it's actually L over 1 plus CE to the negative LKT, but if you remember lice minus licht, that can help you recall where the L goes, where the K, and then there's a negative there. The only thing you have to remember that's not part of this formula here is that there's a plus here. So it's 1 plus. So L-I-C-E minus LKT. All right, notice the prominence of our carrying capacity value, L, in each form of the equation. This is very important, especially when asked for a limit at infinity or when asked to find the y value when the values are increasing most rapidly. And the inflection, whenever it's increasing most rapidly, is whenever we have L over 2, because that is the inflection point. Okay, example 2. The population of Alaska have grown from 1900 to 2000, modeled by this logistic equation, where P is the population and T years after 1900, with 0 corresponding to 1900. What is the predicted population in 2020? So 2020, it's going to be 120 years after 1900. So all we do is plug 120 in for the t value, and that will give us 781,217.6. And we use our calculator now to plug in to find that value. Okay, and the t is here at the end. Negative 0.0516t, maybe kind of hard to read. Okay, part B, how fast was the population changing in 1920, 1940, 1999? So we're trying to find out the rate. Okay, so if we want to find out the rate, we want to find P prime. So to find P prime, we can just simply use our calculator and ask it to evaluate the derivative at 20, at 40, and at 99. So we see that there's always growth, but in 99 we see the growth is at its it's going to be growing at a faster and faster rate as we move towards the present. All right, part C. When was Alaska growing the fastest, and what was the population at then? So growing the fastest, we know that's going to be at its inflection point. It's going to be L over 2. L is going to be the limit, and that's the L that we see. That's going to be the maximum or the limit of the population, 895,000. So it's going to be L over 2. L over 2 is going to be at 447,000 people. So we just set P of t equal to this value and solve for t. We want to find out what is the time when this population is reached. And we can simply use our calculator to determine the time when this population is reached. And it's going to be around t is equal to 82.765 years, or around 1982, 82 years after 1900. AP exam loves to ask questions that require you to recognize the different parameters of logistic growth for either the equation or the differential equation. This requires us to manipulate the equation to fit one of the two standard form below. So we need to be able to go back and forth between the differential equation and the actual population equation. Okay. One more thing here, the maximum sustainable population is given by this L value, 895,598. Okay, example 3. The growth rate of a population, P of bears, in the newly established wildlife preserve is modeled by the differential equation. dP over dt equals ky times L minus y. So if we can recognize this as ky times L minus y, then we can match each of the values. We know k must be 0.008, y is our p, L is 100, and y is p. What is the carrying capacity? Carrying capacity is L. If we know L is 100, then that's going to be easy for us to answer. What is the bear population when the population is growing at its fastest? Growing at its fastest when the point of inflection of L over 2, so L is 100, L over 2, 100 over 2 is equal to 50. What is the rate of change of population when it is growing the fastest? Well, we know that the rate of change, we can just plug in our population of 50 to figure out what the rate is going to be. So 0.08 times P, our population is 50, 100 minus P, 100 minus 50. So plug all this in, we're going to get 20 bears per year. This is going to be when 20 bears per year is going to be the fastest rate of change for this population. Okay, next page. Example 4. Suppose that population develops according to logistic equation. dP equals 0.02 p minus 0.002 p squared. Now this looks similar to the ky times L minus y, but not exactly. So what we need to do is we need to clean this up a bit. If we factor out a 0.002 p, then we can make it 100 minus p on the inside, and that will match up a little bit nicer with what information that we can gather. So if we were to factor out the 0.002, then we know 0.002 is going to be the k, our L is going to be 100, and then we can sketch this graph here. Okay, if P of 0 is equal to 5, what is the limit? The limit is always going to be 100, so it doesn't matter that we start at 5 or we start at 60. If we start at 120, the graph is always going to eventually find its way back to the limit. Okay, even if it's 120. If it's 120, the graph will still eventually come back down to a sustainable level. Okay, so which one has an inflection point? The only thing that has an inflection point is going to be A, because B is going to be too high up. So this is if P of 0 is equal to 5, that's the only graph that will hit the inflection point, which is 100 over 2, which is 50. All right, last example here. The rate at which flu spreads throughout a community is modeled by the logistic differential equation. 0.001 p times 3000 minus p. So from here, instantly we can gather that the k value is 0.001. Our limit is 3,000. If p of 0 is equal to 50, solve for p as the function of t. So we know here is our equation. We just plug everything in. L is 3,000. L is 3,000. K is negative 0.001. Our t value as is. And if we clean this up, we get 3,000 over 1 plus CE to the negative 3t. Use your solution to find the size of the population when t is equal to 2. So we just plug in. First, we need to find the C value. So we know the order pair 0, 50. So if we plug in 0, 50, we can find, oh, actually we haven't finished part A yet. So we still need to find our C value. So plug 0 in for t, and then replace p of 0 with 50. And if we do cross product and solve for c, we get c is equal to 59 because we take 2950 divided by 50. And now we have our p of t, which is 3,000 over 1 plus 59 e to the negative 3t. Now we can go to part B. Use your solution to find the size of the population when t is equal to 2. So we just replace our t value with 2, and that will tell us the population after 2 days, which is, our calculator will be 2,617 people. All right, part C. Find a number of days that have occurred when the flu is spreading the fastest. Flu spreads fastest when it's L over 2. Our L is 3,000. 3,000 over 2 is 1,500. So we want to find out the time when the population will be at 1,500. Once we have that, we can do cross product. And then slowly but surely solve for t. 3,000 over 1,500 is 2. Subtract 1, we get 1. Divide by 59. We want to solve for t by bringing this negative 3t down from the exponent. So take the natural log of both sides. The negatives can cancel. Natural log of 1 over 59. Bring over the negative 1/3. And then plug in our calculator. So after 1.359 days is when the flu will spread the fastest.